Hi, welcome to this brief introduction to software-defined radio. My name is Carl, and together we're going to take a look at what STR is, how it works, and play with some hardware and software. Large parts of this presentation have been shamelessly stolen from some excellent resources across the web. References to them are in the final slide. So what is STR? STR is a radio in which all or part of the physical layer are defined by software. But this isn't just things like the latest version of FLDigi implementing a new weak signal mode. It's fundamental aspects of the radio itself, like filters and a demodulator. Perhaps to see the differences more clearly, we should go back and take a look at a traditional radio configuration. Here we have a pretty standard block diagram of an analog radio receiver. The signal arrives at the antenna and is fed to a mixer stage. There the signal is mixed with a local oscillator, which reduces the signal to an intermediate frequency, typically 10.7 MHz. From there the signal is run through a filter and then a demodulator to recover the audio, and then amplified so we can hear it. In an STR, however, we do things a little differently. In its simplest conceptual form, the signal arrives from the antenna into an analog to digital converter, where it is converted to a digital stream of data and then passed to the software to do all the hard work. Obviously, to make this work, the ADC must produce or handle data at least twice the rate of the frequency of interest. This isn't really practical for the higher frequencies. So we can reduce the bandwidth required for the ADC by putting back a little analog circuitry. The trade-off, of course, is we can no longer see the entire RF spectrum at a glance, but we still do see the bandwidth of the intermediate frequency. It has benefits as well, including lowering the data transfer rate required between the STR hardware and the computer. Well, here is the scariest part of STR, IQ. What does it mean? How much math do I need to know? Well, math? None really, unless you want to. At its simplest, it's just a digital format for transporting frequency and time domain information. Like any data stream, it can be passed between programs or saved to disk as a file. So how do we create it? So, the I part is just the receiver part we saw from a couple of slides ago. The Q part, the quadrature part, is the I part shifted 90 degrees in phase. From this, the software can decode amplitude and phase, and as the data stream progresses, frequency. And to complete the STR receiver, we add a USB interface so we can plug it into a computer. So what sort of hardware do we need? Well, we need a computer, but we don't need much of a computer. You'd run under Linux, Mac OS, Windows. In fact, you can run FreeBSD or Sonos or any particular operating system that can support USB and the software involved. The hardware can be a desktop or a laptop or even a little Raspberry Pi or Orange Pi single board computer. For the RTL dongle or for the STR dongle, an RTL dongle is actually quite a good place to start. Costs about $10 to $50. It can receive one single 2.4 megabits or million samples per second at once. And it has an 8-bit ADC. It's very common and the software is very easy to find. Slightly more expensive and of course better quality, we get the SPI Mini. It's about $130. Again, like the RTL dongle, it's one receiver and a USB interface, but it tunes from 24 MHz to 1.8 GHz, similar to the RTL dongle. However, it has a 12-bit analog to digital converter, and it has a maximum bandwidth of 6 MHz. And sort of in the mid-range, we have the Hack RF. It's got one receiver and one transmitter. It's half duplex. USB interface, it tunes from 1 MHz all the way to 6 GHz. Again, an 8-bit analog to digital converter, but it will actually sample at 20 megahertz, which means you can, if your computer's fast enough, look at a 20 megahertz chunk of spectrum all at once. So let's take a look at some software. There's actually lots and lots of software available for SDR work. There are graphical programs for displaying and listening to signals. There are command line programs, which we'll look at a little bit later on, which you can use to automate some stuff. And there's even GNU Radio, which is, well, I don't touch in this particular presentation at all, but that allows you to assemble building blocks to produce quite complex radios. But first off the rank is Cubic SDR. This is a fully cross-platform, open source SDR receiving. It can handle multiple receivers at once, so you can listen to, say, 2 or 3 airband frequencies at the same time. Development is a little slow. The last release is in 2018, but there does seem to be some activity in the Git repository, so I'm hoping for an updated release soon. It decodes all the normal stuff: AM, FM, FM stereo, SSB, and in fact we'll be looking at this one later. On the Windows side we have SDR Sharp. This is probably the premier Windows SDR decoding program. It's closed source, but it is freely available. It has lots and lots of plugins, so you can decode digital data streams in DMR and so on and so forth. It's actually produced by the company that makes the AirSpy range and is actively developed. GQRX is actually probably my favorite program that I use, but I'm on a Mac most of the time. It's open source, but it does work on Linux and Mac OS only. It seems very simple to use, but development does seem to be stalled. There hasn't been any updates for a couple of years now. On the Windows only front, HDSDR is another excellent one. It's closed source again, but free. It does a few more different modes like ECSSAM. However, it does also allow for transmitting. So if your hardware is capable of transmitting, such as the HackRF, this software will actually drive that and let you transmit. Another Windows only closed source but free is SDR Console. It again, in performance and capability wise, it's very similar to the previous one. And again, it seems to be actively developed. SDR Angel is a very complex and very featured cross-platform open source bit of software. It has plugins for things like DMR, DPMR, D-Star, LoRa, and ATV. It can handle multiple receivers. It is quite complex to use, but very, very powerful. It can also handle transmitters, so you can actually set up if your hardware does transmit capability as well, as some do. This can be used for that, and it is actively developed. And the last one we're going to have a quick look at is the RTL SDR or RX Tools set. They're open source. They're cross-platform. You can get them on Windows. You can get them on Linux. You can get them on Mac. You can get them on FreeBSD. You can run them on your Raspberry Pi. In fact, I do. And they allow you to perform basic functions on the command line. Things like looking and modifying the EEPROM, decoding FM, and then say you want to pipe it to something like Direwolf. RTL Power is interesting. I didn't look at a little bit later on we have a demonstration of this, but I didn't look at RTL Power. It actually lets you sample the power levels right across the spectrum range, like a spectrum analyzer, and then you can load it into something like Excel or some Python to graph it. And RTL Test lets you test whether you're receiving all of the samples from your dongle or not. We'll show that in fact, we'll show that next. So let's actually play with some of this. I have a dongle attached to my computer here, and we'll give it a run. So there are quite a number of tools and programs available for looking at or handling SDR. Some of the most useful ones in the command line for looking at RTL dongles in particular is the RTL SDR toolset or live. There are also variations on that called the RX tools, which take the RTL tools and modify them to support a greater number of SDR receivers. In our case, however, we'll just look at the RTL tools. The first one we'll probably look at, and the most simple, is RTL EEPROM. RTL EEPROM reads the EEPROM from the attached dongle. In this case, it's my RTL-STR.com dongle. It tells me that it's listed as serial number 3, that it's vendor ID 0BDA, and so on and so forth. This is a good test to see if your dongle is connected and whether it can be easily read. Another one you might want to try out is RTL_test. RTL test finds your dongle and then streams data at the maximum rate that the dongle can support, which is typically about 2 mega samples per second, or 2 million samples per second. The dongle itself, the RTL dongles, typically go up to about 2.4 megahertz in bandwidth, or 2.4 million samples per second. If the tool detects that any samples are lost while receiving from this dongle, that will appear here on the screen. As you can see, nothing's appearing, so everything's being read correctly. Get out of it by hitting Control-C, and as it says there, we lost no samples. RTL ADSB lets you listen to aircraft, the ADSB signals from aircraft. Not particularly user-friendly at this point, but you can use this to feed into other ADSB decoding software, or indeed you can pick up something like Dump 1090 or various other programs to decode and look at aircraft signals. RTL 433 is a separate tool, not part of the normal RTL SDR toolset, but one you can install separately. But it actually sits there and listens on 433 megahertz, which is the lipid band. And it looks there listening for lipids, little data transmissions. And there you can see a reception of data from my weather station, showing that it's currently 10.2 degrees Celsius outside with a humidity of 63%. And it's had 327 mils of rainfall since I installed this, which was early in this year. Again, Control-C to get out of this. It also detects things like tire pressure sensors and key fob for your car activations and so on and so forth. Quite enlightening sometimes to see the information that comes through. The last one I'll have a look at is RTL FM. If we set this up to look at a local radio station, I'll set it going, and all that caught on the screen is an audio session, audio being sent from RTL FM, which you can then use something like SOX or Play or similar command line to listen to an FM radio stream. Not the easiest way of doing that, but certainly quite useful and quite interesting, because you can then feed that, for instance, into Direwolf and use that to decode APRS packets or similar. So here we are looking at the interface for Cubic SDR. When you start the program, it gives you a selection of inputs to use. If you've already got a IQ signal being delivered from an audio card or something similar, or another computer, you can use one of the other inputs. But in my case, I'm going to use the generic RTL dongle input here. I also have my HackRF1 connected, but we won't use that just yet. You click on Start, and the signal decoding starts. At the moment, we're listening to the FM radio band again. There's 101.5. You can see the signals there. You can also see the bandwidth here is 2.4 megahertz. That's the sampling range of the RTL dongles. It can see 2.4 megahertz in a single slice, or you can shrink it down lower if you want a finer resolution. In this case, you can also zoom in on the singles to give you a finer resolution in the software itself, so you don't actually have to worry about modifying the sample rate unless you particularly want to. So you can see here at 99.9 there is a signal.
This border control states that seasonal workers are not critical workers, and seasonal workers are expressly forbidden from crossing the border. Now, I think there's a lot of confusion within the New South Wales government.
So we'll just mute that. As you can hear, it's actually listening to the radio. That's actually FM, not FM stereo. We can convert that to FM stereo. Australia uses a 50 microsecond de-emphasis on our FM radio. And we should get stereo audio. Not that you can hear that in a spoken word.
And just getting pushback to the health plan, which just doesn't take into consideration.
We can have multiple signals operational in cubic SDR. So it's useful if you want to listen to multiple frequencies. You can set a squelch over here on the right. Up here we have the actual stereo signal, the audio side of it. Here we have the individual signal being shown, and down here we have the full bandpass of the RTL dongle. On the left we have different modes, and on the bottom left down here we have bookmarks. So for instance, if I want to listen to the Canberra Tower, I'll remove this active one at the moment, double click on the active Canberra Tower, and now we're listening at 118.7, the squelch. We're still muted, that's why. We do have a squelch option available here, but there's no signal. And in fact, it's quite hard for me to listen to Canberra Tower from where I am. There's a massive mountain in the way. So you can click on the bookmark and then remove active. That will go away and we will stop. We can also, for instance, listen to various ham radio frequencies, 439 megs, just by double clicking on that. There's the squelch side of it. That's the volume side. Solo mode, we'll leave that alone. There's the squelch. At the moment it's listening to 439 meg in FM, and it's there's no audio there at the moment, so we can see how that works. So here we have GQRX. This is available for Linux and for Mac OS. I don't believe it's available for Windows, but you can have a look if you like. To get it running, click up here, select the input device. I've got the Realtek input device selected. Click OK. One thing I do want to do is change this frequency correction here to 0, because the SDR dongle I'm using at the moment is the RTLSDR.com device. That has a very good frequency accuracy. It's got a TXCO on it. The other RTL dongles I've got a couple of others, are quite cheap, and they're actually the DVB-T dongles rather than something designed for SDR. And one of them is 88 parts per million out, the other one's 49. So once we've set that up, we just hit start, and away we go. As you can see here, we're listening to 125.9 megahertz, which is just here where this particular bit is. If I go over to receiver options, I can see we're listening to AM, and the squelch is set there. Very faintly hear some audio there for the squelch. 125.0 seems to have a signal as well. Yeah, that's not good. Let's not listen to that. So that's as simple as this one is. This one's actually one of my favorite SDR programs to use. It's very simple. It has some good basic features. Frequency control here, input control here, including things like whether to use a Harbour AGC, whether to put in the low noise amplifier. FFT settings here where you can actually change how the program decodes a signal, and some audio view output here. It also has the ability to do screenshots and remote control and so on and so forth. It's quite good. It's very basic but fully functional. And if you look in the receiver options, it'll actually do quite a lot. Narrow FM, wide FM, sideband, and so on. And the last thing we'll look at is a program called well.io. It's also the name of the website to obtain it from. This is a DAB Plus receiving software designed specifically for the RTL dongle. And with the recent move to production of DAB Plus broadcasting in Canberra and the resulting increase in transmitter power, it actually works very well, and you can hear all the signals that are available. Even here where I am behind a ruddy great mountain from Black Mountain Tower, you can see I can see all the signals and get a decent receive of all of them. There are quite a few signals on there, including things like the Edge, which is the Snow DAB Plus, which is Snow Mountains. The Edge and Triple J are all Triple J. Club Line Radio, okay. Coles Radio, I really don't know. Let's just pick one at random. Let's pick RPH. It's the Print Handicap Radio. They should be reading the news about now. Double click on that. Syncs up.
Giant Gippsland earthworm, however, is one of the most famous because of its sheer size.
I'm not going to dispute that. But as you can see, we're currently decoding 48 kilohertz stereo using the HE AAC AAC-V2 codec. If there's pictures available in the DAB Plus, and they'll appear here. And you can see that my dongle is sitting at minus 1.04 parts per million off, so I probably should put that into the correction factor, but minus 1 part per million is naff all, really. Well, that concludes this introduction to STR. I shamelessly ripped off content from everyone listed on this slide, especially from Ken Pakago's excellent presentation for the South Towns Amateur Radio Society. Thank you very much.